Hello, and welcome to this episode of State Machine Corner. I'm Dr. Bruce Powell Douglas, Senior Principal Agile System Engineer at the MITRE Corporation and Principal at A Priori Systems. Today, in Episode 6, we'll be talking about AND states. In previous episodes, we've talked about different aspects of state machines. In the last episode, we talked about nested states. AND states extend the notion of nested states and are particularly valuable for representing and modeling the behavior of objects that have concurrently active aspects that are more or less independent of each other. Here's our agenda for today. We'll start off talking about nested states to revisit our discussion. Then we'll talk about basic AND states, how to render AND states in Rhapsody and Cameo, a bit more about AND state semantics, how to model collaboration between AND states, alternatives to using AND states, the use of forks and joins, and we'll wrap up with a discussion of race conditions. To start, let's consider nested states once again. So here we have a Rhapsody model. There's a block here called sensor, and it has some operations and event receptions. This is the state machine for that block that describes the sensor states. It can be off or it can be on. And when it's on, it can be waiting to start or operating. And when it's operating, it can either be waiting for data or processing data. A simple nested state machine. So when it's off, it receives the EV on event and goes into the waiting to start. And inside, there are operations. It's an operation when it's off to print the light is off to standard output. When it's waiting to start, it prints initializing and the light should be blinking. When it goes into operating, it starts in the waiting for data state with a steady green light. When data arrives, the light becomes steady red and it processes the data. And after 2 seconds, this is my 2-second timeout, it goes back to waiting for data. Up above, I've developed a panel diagram. The buttons insert the events to the object. The EV on, the EV off, EV start, initialize, data arrives. And so I've added some LEDs, the color code. These are tied to the different states. Let's run this state machine. We'll kick it off. And it starts in the off state because that's the default. From here, with my panel diagram, I can insert the EV on event and it transitions to the on state and its default nested state, which is waiting to start. When it enters, it executes the behavior, print initializing, and print blinking light. If you look in the output, we see that started off with the lights off, it's initializing, and then goes to blinking light. If we look at our panel diagram, we see the light is blinking. From here, we can insert the start event, EV start, and that transitions from waiting to start to operating and into the internal nested state waiting for data. At this point, we've printed out steady green light. We see that over here, steady green light, and we see our panel diagram as a steady green LED. Now, when I click the button to insert that the fact data has arrived, insert that event, then go to processing data, it'll print out steady red light, processing data, and after 2 seconds, it'll transition back. So this light will light up red, and after 2 seconds, it'll go back to green. Let's see that. So it's red for 2 seconds, and it goes back to green. And we see that's exactly what happened. Let's watch that one more time. Data arrives. It goes to processing data. After 2 seconds, it goes back to waiting for data. From here, I can reinitialize. And in fact, I can also turn off. We can do the very same thing in Cameo. So this is the same model, done in Cameo. Here we've got our sensor block. We've got the state machine with the off state, the on state, and the nested states, exactly the same way we had it in Rhapsody. Let's run this. Now I've created a panel diagram in Cameo as well, using a feature called Image Switcher to show the light. And the light is currently off, and that's in fact what we see. Here's the console output, light is off. From here I can insert EV on, and I go to the waiting to start state, and now we have a flashing light, just like we expect. We can insert the EV start event, and we go to waiting for the data, and we see a steady green light. If I insert the EV data arrives event, it'll go processing the data. The light will be red. After 2 seconds, it'll go back to waiting for data. Let's see that. Light's red, 2 seconds goes by, it goes back to steady green light, and we see the same is going on in our console output here. Let's do that one more time. Goes to red, 2 seconds go by, it goes back to waiting for data. We can also reinitialize, and we can turn it off. So remember, these are OR states. This object is either in the off state or the on state. No other possibilities exist. When it's in the on state, there are 2 nested states. It must be in exactly one of those. Waiting to start or operating. And if it's operating, it must be in one of its nested states, waiting for data or processing data. And in fact, this diagram shows 3 different levels of abstraction of the state machine behavior. Off versus on, waiting to start versus operating, and waiting for data versus processing data. And that's how nested states work. At the very core is this concept of OR states. Now, if you're in the operating state, for example, these states are exclusive. The object may be in waiting for data or processing data. It can't be in none of them, and it can't be in 2 of them. It has to be in exactly one. That's what we mean by OR states. We will bend that rule when we talk about AND states. So let's talk a little bit about the semantics of AND states. AND states are nested states. They're nested within a composite owning state. In the same sense that OR states can be nested within a composite state. The difference is that with AND states, every active AND state is concurrently true. In OR states, when you have nested states which are OR states, only one of them is true at any given time. When you have nested AND states, they're all simultaneously true. So when a composite state owns multiple AND states, and the object is in the composite state, the object is in every AND state owned by the composite state at the same time. Because AND states are states, they can contain nested states themselves. And this is almost always the case. That within an AND state, you'll have nested states. And these mostly will be OR states. You must identify the default in every AND state so that the execution is well defined. So when you go into an AND state and you've got multiple OR states inside there, where do you start? That must be defined. Default state must be defined for all the active AND states. But the object will be in one of the nested states in every active AND state owned by the current composite state. AND states are logically concurrent. That means that they're simultaneously true, and they can receive events and process events. The state machine step is a step for the entire object, not for a particular state. So the state machine step is complete with OR states when you've completely processed an event, that is, you either discarded it or you've taken a transition or done some behavior based on that event. When you have AND states, the same is true, but all of the AND states have the opportunity to act on that event. So you can think about it that every event is replicated or copied and sent to every active AND state. So if you've got 5 nested AND states and you send an EV1 event, they're all free to act on it or discard it. And the state machine step isn't complete until they've all properly processed that event. Now, because they're logically concurrent, you don't know which of the AND states will process that event first. So you need to be careful not to build in dependencies on order execution, or you'll incur race conditions. Now, just because these AND states are logically concurrent doesn't mean that this is how you would model threads for a software concurrency architecture. That's not, in fact, how you would do that. Rather, you would rather use active objects. An active object is an object that owns the root of a thread, and it executes in that thread. And all state machines within that thread share a common event queue for all of the events coming into that thread. I plan on a future video talking about concurrency architecture with UML and SysML. So let's see how we actually add AND states in Rhapsody and in Cameo. Let's start by adding a state here. I'll make it nice and big, and we'll call it composite state. And I'm just going to add a few states. Move them around a little bit. We'll add the AND state lines. So here's the AND state line in Rhapsody. We'll add our AND state line from here to here. And then I'll add the AND state line to separate these. And now we can add our transitions between the states. And so on, just like you would in a normal state context that you might have. You do need to add a default transition in each one of the AND states, unless there is only exactly one state within an AND state. And now we can add transitions here. We go from state 7 to state 6 based on EV1 and back on this, maybe on the same event. We can go between these two states based on other events. And then we could transition from state 0 to the composite state based on some events like EV start. So a couple things to note. These AND state lines are dashed lines that separate these orthogonal regions or AND states. So these are the regions or AND states. You can give these names and expose those as a display property if you want to. By default, they're not exposed. You must identify the default starting state in each one of these AND states. And notice that it's okay to have the same event trigger transitions in different end states, as many end states as you want. When you're in state 3 and you're state 6 and you're state 9 and an EV1 is received by the object, every one of these end states is given the opportunity to execute that transition based on that event. In this case, there is no EV1, so this lower end state would just throw it away. In this case, it would go from state 6 to state 7 or from state 7 to state 6. And in this left upper end state, if it's in state 3, it would transition and go to state 5. The state machine step isn't done until all of the end states have had the opportunity to either discard the event or act on it, whichever is appropriate based on the state behavior defined. What you don't know is which one of them does it first. So if they all act on EV1, let's add one here, transition. Could be that all of these end states all receive the EV1 and process it, but I don't know which order they occur in, and that's crucial. Let's do the very same thing in Cameo. So I'm going to add my new state, and I'll make it bigger like we did before. I'll name it composite state. And now let's add some states. So I'm going to take the stamp tool like I did before. We'll add some states. Turn off my stamp tool. And now I want to add some orthogonal regions. You do it differently than you did in Rhapsody. There are a few ways to do this. The easy way is to click on the plus right here, and that adds this region. And then we can drag states into that region. Once we do that, we can adjust our end state line. But there's no way we can add a vertical line like we can in Rhapsody. Personally, I find that a little bit annoying, but fine. What we can do is add another stacked end state, vertical end state. Here's our region here, and do it this way. Now, if you've only got 2 or 3, it's not such a problem. But if you had 5 different end states, the inability to stack them to the right and left, as well as up and down, is a problem. Just drawing the diagram. Once you've got that, of course, you name the states. I wouldn't bother to do that, but you can add your transitions. Here we have EV1. From here, I don't remember exactly what we did before, and it doesn't really matter. It's going to be EV2. From here, we can do EV3. And so on. Over. From here, we had EV1 going back and forth, so I'm going to be a little bit bigger. A little more constrained with the geometry in Cameo. And now we do have to define the default in one of the end states. Slightly different than you do it in Rhapsody. You drag the initial state and then you separately add the transition from that initial state. So drawing it is slightly different in Cameo than in Rhapsody. So let's look at an example of a AND state. So here I've got an LED package in Cameo with a colored LED underscore nested with nested states. We open that state machine up. There we go. We see that it's got 3 AND states in the ON state. It's got one which is focused on the color of the LED, be red, yellow, or green. The middle one focuses on the flashing rate, steady, flashing quickly, flashing slowly. And the bottom AND state is focused on bright or dim. So we can go on, in which case we go to the default of each one of these nested states. Let's go ahead and run this simulation. And we'll kick it off. And we can see we're started off in the off state. I can now insert the go on event. And it transitions to the red, default color, steady, the default flashing rate, and dim, default brightness. And then we can send it events. We can say, okay, well, in terms of color, we can go to green. Here's go green. In terms of the flashing rate, we can go to flashing quickly. And in terms of brightness, we can go to bright. Where's bright here? Here we go. Right. And then we can transition back. We can go from steady or from currently flashing quickly to flashing slowly. So we can go slowly. Go slowly. Here we go. We can go back to dim. And we can go back to, we can go to yellow. Let's go to yellow here. Now, regardless of which state I'm in, I can go off and it'll exit every one of these AND states because it'll exit the ON state. Let's go ahead and do that. We'll go off. And you see we've exited back to the off state. Now, if I go back on, whoops, wrong events, go on. We now enter our defaults. Let's go to say the yellow state. Go yellow. So now we're in yellow, steady, dim. If the object receives the event, it's too bright, what's it going to do? Well, it's currently in a dim state, so it's going to throw that away. But let's just make sure. So it's too bright. Doesn't do anything, throws it away. Exactly what we expect. On the other hand, if I get the event, we don't like yellow, it should exit, and it'll exit regardless of what nested state it's in the other AND states, because its precondition state is true. And that's in fact the behavior that we see. We can do exactly the same thing in Rhapsody. Here's the same model in Rhapsody. It's organized pretty much the same way, other than we have state over on the right-hand side rather than being vertically stacked. And this executes the same way. Let's go ahead and run it. And we see we go up into the off state. Then we can use our insert events, generate an event dialog here. We can go to green like we did before. We can go green. Oops, first I have to turn it on. Let's turn it on first. Go on. Here we go. Okay, so now we're in each one of the nested states. Now we can go green. And we can go flashing quickly as we did before. Go quickly. And we can go to bright. Cool. From here we can go to yellow as we did before in the previous Cameo example. So we can go yellow. And we can go to flashing slowly. And we can go to dim. Now, as before, if I say it's too bright, that event will be thrown away because we're not in the right predecessor state. We're currently in the dim state. Let's go ahead and demonstrate that. We don't like yellow. No, it's too bright. Here we go. Generate the event, and nothing happens. But if we don't like yellow, because it is currently in the yellow state, we expect to transition to the off state. And in fact, that's exactly what happens. So it works exactly the same way that it did in Cameo. So understand that you never have to use AND states. There are alternative approaches that are completely behaviorally equivalent to using AND states. So when should you use AND states? When to simplify the overall model. As I mentioned previously, I think that there are two kinds of complexity. There's incidental complexity and there's essential complexity. Essential complexity is how hard the problem is you have to solve. And you can never get below that. Incidental complexity is complexity that is due to how you've chosen to solve or address or represent the problem. You want to get incidental complexity as close to zero as possible. When AND states reduce the incidental complexity of your model, then AND states are appropriate. So some alternatives. You can always flatten the state machine. With AND states, that means that you will produce the cross product of the state space. So in the case of our LED, you'll produce states like red, flashing quickly, dim, green, steady, bright. All those products from the different independent AND states are potential states that you have to represent in your flattened state machine. We'll see what that looks like in just a moment. Another option is to use separate blocks. If you use this approach, you'll have an owner block, in this case LED, and the various AND states will be represented in a separate composite owned block, one per AND state. So in this particular case, we'd have an LED, and then there would be a color block that receives and processes the color events. There would be a rate block that receives and processes the rate events, and a brightness block that receives and processes the brightness events. Now the owner block would receive the incoming event, and it would then delegate to the appropriate composite part for processing. Sometimes that simplifies the model, and sometimes it doesn't. Some people say you should always do that. I am not of that opinion. Do it when it simplifies the overall complexity. When the parts are loosely coupled in terms of resources owned by the owner block, that may be the best way because they're loosely coupled. When the blocks or the parts are relatively independent of each other, the AND states are really independent, also, that's a case where it might simplify the overall problem. Another option of representation is really to still use a nested state machine with nested AND states, but show them often separate state machine diagrams. And this is really to manage diagrammatic complexity. When you do that, those diagrams that are inherently nested are called submachines. So use submachines when you want to simplify the overall diagram, but still maintain these different AND states on the owner state machine. All right, so let's see what that looks like when you flatten the state machine. So here is the original state machine with our three regions: color, region, where I've exposed the color, rate, and brightness. What does that look like as a flat state machine? Yeah, that's what it looks like. So if you look a little more closely, we see that there are states like green, steady, dim, green, steady, bright, red, steady, bright, red, flashing slowly, bright, red, flashing quickly, dim, green, flashing quickly, bright, yellow, flashing quickly, bright, yellow, flashing slowly, dim, and so on. So all of the states are represented as a flattened state machine by producing the cross product of the state spaces. Now, this is exactly equivalent to the previous state machine. Or is it? Did I miss a transition? How would you tell? So I think clearly in this case, it is more complex than with nested state machines. But let's go ahead and execute this. So we got our state nodes. We'll go ahead and run this. Start it up. And here is our flattened state machine. We can open up the instant state machine here. And now we can do the same sort of thing we did before. We enter in our events. So let's get our event generator. And the first thing we want to do is we want to go on. So let's say already selected. We'll go ahead and insert that to our flattened state machine. And here we go on. So we go on into the state of red, steady, dim, which was our defaults. From here, we can go green. Remember, we did that before. So we can go green. We transition to there. We can also then go from steady to flashing quickly. So go quickly. And from green, flashing quickly, dim, we can go to bright. So send the go bright event. We can go to yellow, so go yellow. And then from here, we should be able to say, we can go off. And from any of these states, we can go off. Or we can also, from this state, do the transition, we don't like yellow. So let's try that. We don't see that in the list. We forgot that. Was it obvious too that we forgot that? Wasn't obvious to me, but we can certainly go off, and that should take us back to the off state. So it illustrates the point that it's much more difficult to get something like this working in this case with a flattened state machine than with the nested states. The second means for representing the behavior without nested AND states is shown here. So here's our nested AND state machine. The second means was to use a composited block. So here we've got our colored LED underscore composited, to call it out. It's got three parts: a rate part, a brightness part, and a color part. Note the role names or the reference property name here. Its rate, its brightness, its color. We'll need those later. Each one of these has a state machine, corresponds to handling the events for rate, the events for brightness, the events for color. There's also a state machine for managing and delegating the behaviors in the LED itself. So let's look at these state machines. Start off with rate. So here's our rate is here. So as before, we have steady, flashing quickly, and flashing slowly. Well, we've had to add an off state to this because what state should it be in when it's not on? It should be off. So we've added a new state. And we've also added a number of transitions to go from each of the kind of semantic states back to this off state. Go off here, go off here, and go off here. Otherwise, it's pretty much the same. For brightness, we had, remember, two nested states, dim and bright. When it goes on, it goes to the dim state. That was the default. But we also have to add an off state. When it's not even on, what's the brightness? Well, it's in the off state. It has no brightness. And so we've added an off state plus a couple of transitions to go off from the bright and dim nested states. So already it's a little bit more complex than we had before. And similarly, for the color, we have red, yellow, green, just as we had before. We had to add an off state as well as 3 go off transitions, so that regardless of which nested state you're in, you go to the off state. So it's a little bit more complex. We added 3 states so far to manage that. And 8 transitions, 8 go off transitions to do that. But okay. Now, an interesting question is, what about this composited state, the LED itself? Remember, this is going to receive the events. You know, change the rate, change the brightness, change the color. Any clients of this LED should not know anything about the internal structure of the LED. That would just be bad design. You know, Parnas in 1960 published a paper on why encapsulation was a good idea, and it remains true today. The clients of the LED should not know how color, brightness, and rate are implemented. That means that those events go to this LED block, and it then must delegate them to the appropriate part and manage those events. So let's see what that state machine looks like. That's this. We can make this a little bit prettier here. So, starts off in the off state of the LED. When it goes on, it sends the go on event to the brightness here, and so it goes dim, to the color part here, so it goes to red, and to the rate part, so here it goes to steady. So the defaults are preserved. And then it goes to the waiting state. Then from here, when it receives an event, it delegates it off to the appropriate part. So these are, of course, send actions. So if it gets the go dim event at the LED level, it then delegates to its brightness part. And that would be here, if it goes dim, it would get this event to go dim. So if it's bright, go dim, goes in the dim state. Similarly, if it gets to go yellow, it says, oh, well, the color handles that. So it delegates it off to its color. Its color is here. So suppose we're red and it gets the go yellow event, it would then transition to the yellow state, just as it did with the nested states. So that's okay. All this is really delegation management of the parts, and so they receive and process the events. But there were a couple of other events, weren't there? There was, it's too bright. Now when it's too bright is received, it turns off, but only if the bright is true. So here we see, let me zoom in on that so you can see that a little bit better. It's too bright, it goes from the waiting state to off, and it tells everybody to go off, but only if its brightness is in the bright state. So Rhapsody provides an is in helper macro that will return true if the object it's being referenced to, in this case its brightness, is currently in the stated state. So if it is in the bright state right now, when the guard is checked, it will return true, and this will be properly processed. Similarly, we don't like yellow has an effect if the color part is in the yellow state. So again, the is in macro is applied here as well. So how does this work? Well, let's see. So let's go ahead and run. Kick things off. And we see everything's in the off state. That looks good. Let me resize things a little bit here. All right, so now this is the object that will receive the events from its clients. So we will open up the event generator dialog for that. And let's insert some events. So let's go on. So here's the go on event. And what I expect it to do is take this transition and send an on to brightness here, an on to color here, and an on to rate here. And in fact, that's what it does. And then from here, if we go green, like we did in the previous exercise, we go green, we would expect to go green, should activate, and then go from red to green. And in fact, that's what happens. We can also get go flashing quickly, so go quickly event. And we process that here. And we can go from dim to bright, so we go bright here. Now, if I get the event, we don't like yellow, it should be thrown away. And in fact, that's what happens. In fact, that is nothing. But if we transition to yellow, then do that, we expect it should go off. Let's see if that happens. So let's go yellow. Now it's in the yellow state. We see that's the active state. And now we don't like yellow. It should go off. Everybody should go off. And in fact, that's what seems to happen. Now I would argue that this is not a simpler state machine than the nested states. Remember, the nested states looks like this. This, I believe, is simpler than these states. And if you do a number of states and number of transition counts, I think you'd find a very significant difference. But this is an alternative, where we instrument the main block, add part blocks with the state machines for the AND states, and the main block then delegates the events off to those parts for processing. The last approach I mentioned as an alternative to AND states was to use submachines. Now, semantically, submachines are identical to having the nested states. So logically and semantically, they're actually in place. But for diagrammatic complexity reasons, we're going to expose the details on another diagram. So here we see the very same state machine with submachines, off and on, and the color and state is shown as a submachine, which I can get to by clicking this icon in Rhapsody. There's the rate state machine and the brightness state machine. So all the internal states are hidden from view here, although I can merge those back in and open it back out very easily in Rhapsody. It's a little bit more of a pain in Cameo, but it can still be done. So now remember, there were a couple of cases where we're not relying on default behaviors. In the color state, we only process the "we don't like yellow" event if it was in the yellow state. So normally, and if it was in place here, I would just draw that transition from that nested state inside this AND state to the off state, and I'd be done with it. However, there's nothing to draw to. So in that case, we use exit or entry points. In this case, they're both exit points. So I named these yellow exit point to go from the yellow state, and the bright exit point to go from the bright state for the "it's too bright" event. Let's see what that looks like in the nested states. So this is the rate. It didn't have entry exit point, so let's look at that first. It's the same. Default steady, and we got flashing quickly, flashing slowly, same state machine we saw before. So that's really no change. It's just instead of being in the end state, that rate and state is shown here. Now for the brightness, you remember that there is an exit point. So it starts off in the dim state as before, and we can go bright and go dim. And if it gets the event, "it's too bright," it goes to that bright exit point. This is how it connects across that diagrammatic boundary, is through this exit point here. And we see the corresponding point here, bright exit point. Similarly, for the color submachine, we start off in red and we can go between red and yellow and green. And if it's in the yellow state, we get the "we don't like yellow" event, we go to the yellow exit point, which is this path here. So that's entry and exit points. I do plan on talking in the upcoming video on submachines more about entry and exit points. So let's see how this works. If I need to recompile, I do not. Let's go ahead and run this. Here we start off in our off states, and we can insert events again at the highest level. So we'll add our events generator. We generate events, and the first thing we'll do is we'll go on. And so we expect to go to the steady state for rate, the red state for color, and the dim state for brightness. Let's do that. And in fact, that's what we see. Now, unlike the composited version, we actually had to delegate responsibility, but this is logically in line. So we don't have to do anything like that. It's just in place. It's just we've chosen to expose it in a separate diagram. So now we can go green. And here we go to the green state. We can go to quickly, flashing quickly. I can go to the bright state. I can then go to yellow. We're in yellow. And now I can send the "we don't like yellow" event if I want. And I expect this transition to activate and end up in the off state. And in fact, that's what happens. So submachines are an alternative approach. And you can use this, again, to manage diagrammatic complexity when it's useful. The next topic is forks and joins. So here we've got a state machine with a ready state, initializing, running new setup, and error state. When we take the transition EV go new, we go to the initializing state, which has two AND states. In the upper AND state, we load the map. We load a new map. After we get the EV initialized nav, we go to the initializing nav system state. After we get the EV done initializing nav, we go to the ready nav state. In the lower AND state, we go to loading communication protocols, loading COM protocol state. Then we have an event EV init comms. So we initialize our COM devices in this state. And then when we're done initializing COM devices, we get that event, we go to ready comms. When I take the EV go new transition, the object goes to load the maps, initialize COM protocols. Now, what if I want to bypass both of these default states? I want to use the previously loaded map, the previously loaded communication protocols. How would I do that? How would I draw the transition from the ready state to those target states? If it was just one, I could do that easily enough, and the others would use it as a default. But in this case, I want to bypass the default in two AND states. To do that, I need a fork. A fork is shown as this heavy line. That can be either vertically or horizontally oriented, with a single incoming transition, triggered by a single event, and then terminates on multiple AND states. So it has to go from outside the AND state, the composite state owning the AND states, into the AND states. So in this case, EV go using previous values. It doesn't load the map, it uses the existing loaded map, and goes directly to initializing nav system. And it doesn't load communication protocols, it uses the existing ones, and goes to initializing COM devices. Now, we've seen before that I can go from a single nested state out, and the other AND states are don't cares. Whatever state is in the AND state is true, it's fine. But what if you want to trigger a transition only if multiple states are true inside different AND states? Then you need a join. And so this is a join. It looks much like the fork does. It's slightly different in Cameo, but it looks very much the same. A point to remember that this transition fires only if, one, that the triggering event is received, and two, all of the predecessor predicate states are true. So if the object receives EV start operating and is currently in both ready nav and ready comms, this transition is taken. If it's in ready nav and initializing COM devices, this event would be thrown away because its predicate predecessor conditions are not met. Now, we've seen before with the we don't like yellow and it's too bright events. If I want to go from this state out, I can do that. And then the other ones are don't care, right? But in this case, this transition will only fire if the event is received and both of these states are true. And there can be more than just two AND states here. So how does this actually work? Well, let's go ahead and run this. So I've created a little panel diagram to help me do the execution of this. And let's start it up. Start off in the off event. If I go new, here's go new, starts off there, and now I can say EV init comms, EV initialize nav. Done with those two, and then I can trigger the EV start operating, as I expect. Let's go back, let's stop this, go back to here, and now let's bypass the default by going using previous values. Now if I try to start operating directly, it'll fail because predecessor events are true. Even if I initialize the nav, or done initializing nav rather, and try that, still won't work. But once I go initialize the comms as well, now it will work. Okay, so forks and joins. So end states are relatively straightforward. I mean, there's a lot there, but they're relatively straightforward when they're independent. What if they need to collaborate? Life gets a little bit more complex. So there are a few ways in which they can collaborate. First of all, the first one you already mentioned is what I call broadcast events. Now these events are not broadcast between different objects, but this is just meant to point out that when there are multiple active AND states, every AND state receives basically its own copy of that event and is free to act on the event or throw it away as appropriate, and the state machine step completes once all the end states have processed that event. So I call that broadcast events. When we do this, we don't know which end state will process an event first. But what if I want the upper end state to process an event first and the lower end state to process it later, or vice versa, or I want to enforce a particular order? Well, there's an idiom, state machine design pattern, called propagated events. And the way this works is that you only accept the event in one AND state, and as part of its behavior, it sends event back to the same object, another event, that is then handled in the next run to completion step. So we propagate the event forward. So that way, even though logically perhaps multiple AND states might respond to the events in the same events, but we want to enforce a particular order, we make up additional events and send them to ourselves to enforce a particular order. Another way that AND states can collaborate is with guards. And we saw this before with the Rhapsody, where there's this is-in macro, references a state, and if you've got two AND states, it can reference a state perhaps in another AND state. So only power the microwave emitter when the door is closed. It's in the door is closed event, or state rather. So you can use the is-in macro for that. Cameo has something similar called in-state. So the syntax is shown here. So it's action language helper dot in-state, and you pass it the name of the state as a string. In Rhapsody, you just use the name of the state. But in Cameo, you enclose it in quotes. It's a string, and reference the state in the other AND state. So you can use guards to coordinate the response. Only do it if this state's true. And lastly, we have attributes. So attributes or value properties in SysML are properties that have values. And because the scope of a state machine is the entire part, the entire instance, all the states see all the attributes. And so they can use stuff based on those guards. If x is greater than 0, do that. In the other AND state, if x is greater than 5, do this. You have to be a little bit careful with resources. We'll talk about that in the next section, race conditions. But attributes is another way you can communicate and collaborate. So here's an example done in Rhapsody that shows some of these things we're talking about. So notice that we have the E1 event. It's used in both of the AND states. Here it is here, here it is here. All right. And so that's what we consider to be a broadcast event. In the E2 event, here's E2. We print out what we're doing, and we see generate EV propagated. So this EV propagated is an event, and we haven't specified where it goes. So that means that we sent to the same object. In the lower end state, here we see EV propagated. So in one step, it'll process the E2 event, and the object will send itself EV propagated. And in the next step, it can accept the EV propagated event and transition. So that's the propagated event. We can also use guards. So here we have A2 going to A1, triggered by E4, and we have the guard is in B3. So this transition will only be taken if the object is in B3. And here we have the E5 event, E5 not, here's a bang operator, not is in, let me zoom in so you can see that a little bit better. Not is in A3. So you can also do not conditions as well. So this transition is only taken if the object is not in A3. So let's run this, see how this all works. Let me make more room here so we can see the output window here. And let's start it up. So let's do the first case, broadcast events. Let's do the E1 event. So let me, again, load in my event generator. And we'll do the E1 event. Takes a transition. Okay, let's do a restart. We'll go back to our defaults. And we'll take the E2. So what I expect is in the first case, it'll take the this transition, and in the next step, it will take the propagated transition. Now we're going to change how we're running so we can see how it actually works. So we're going to pause this, and we're going to do events, an event at a time. Let's generate the E2 event. It's currently paused. Generate, so that event is waiting. And let's do a go event. Go event. And here we see we've sent the propagated event. We're now in the E3 state. If we look at our waiting pending events, we see that there's actually an EV propagated event pending. And if we do that again, then we'll take that second transition. So that's propagated events. The third thing we're going to talk about is guards. So let's go ahead and restart again. Back to our starting case. Oops, have to run. There we go. So now let's take a E1. So now we're in the A2 state and B2 state. Now if I get an E4 event, nothing should happen because it's not in the B3 event. Or not in the B3 state rather, right? So nothing should happen. Let's go ahead and try that just to see. E4. Nothing happens. So now let's go do the event to B3 to put it in B3. And now we'll do the E4, and I expect we'll go back to A1. I love it when a plan comes together. Now the other case was E5. E5 is taken only if the object is not in A3. Well, currently it's in A1, not A3, so this should fire. Let's go ahead and do that, and that's triggered by E5. life is good. And we'll talk about the attributes in the next section. Now here's the very same state machine, basically done in Cameo. See, we use simple properties to expose the fact that there are A states here and B states down here. But we can also run this. And we should see basically the same behavior as before. Let's kick this off. We're in A1, B1. We do an E1 event. It transitions to A2, B2. That's fine. Let's do a reset. Go back to where we were. And now if we do E2, we expect that it'll do the propagated event here, and then it'll be consumed in the next state machine step here. Now remember that on Rhapsody, we actually send action on the state machine. Can't do that in Cameo. So in Cameo, I added an activity. If we look in the state machines here, under A3, here's my activity. It's not particularly interesting. It just sends a propagated event. So not all that interesting. But I can't do it on the state machine diagram per se. Another joy that is Cameo. But that's the behavior, the entry action here. I send that action here. And so in the next state machine step, I process it here. So let's see that if that happens. So we're in A1 and B1. Let's go ahead and do the E2 event. And in fact, that's what happens. The next thing to check was the, so that's propagated. Third thing was the guards. So here we have the action language helper.isIn. See in quotes B3. Let me zoom in just a little bit on that. So ALH.inState quotes B3 is referring to the B3 state down here, right? So if we are currently in A3, so let's go to A2. So now we're in the A2 state, and we're currently in the B3 state, so we expect to be able to take that transition. So let's do an E4. And in fact, we see it transitions to the A1 state here. Cool. Now we're in B3, we have the E5, bang, ALH.inState A3. So it's not in A3, so this guard should return true. And I should be able to transition from B3 back to B1 with that E5 event. And in fact, that's what happens. So it works both in Rhapsody and in Cameo. The last topic I want to talk about is race conditions. Now, a race condition is a condition in which a computational result depends upon an order of execution that is, in principle, unknowable. Now, remember we talked about AND states. Well, I said that when an event is received in multiple AND states, the same event, when you have multiple active AND states, you cannot know in principle which is executed first. And these manipulate values, such as value properties, that can lead to race conditions. So let's look at an example. So here we have a Cameo example where we've got a ready state with an entry action here, the transition action going in, where X of value property is set to the value 0. And then you get to go event. And then we've got two AND states. One called augment, which augments X by 1. And one which scales it and multiplies it by 100. And then you get the EV complete event, and you go to the done state. So as soon as we go EV go, This state machine will execute this, and it will compute a value for x. But we can't in principle know what it is. A particular tool implementation may decide to do the upper one first, the one you drew first, the one you drew later first. It could randomly select which order to choose, all of which would be compatible with the standard. You inherently don't know which of these will execute first, and that's a race condition. So let's execute this and see what it does. So we're in ready state. We see x currently has the value 0. You see in the value variables area down here. If I take the transition EV-go, it executes this and executes those two states. But we can't enforce which one happens first. The value we get is 100. That means it did the upper one first in this case. But we can in principle count on that. And then when we take the next event, which you complete, then it prints out the result here. So that is a classic race condition. Rhapsody is exactly the same way, works exactly the same way. So my recommendation is don't do that. There's a law of Douglas, which says that any language rich enough to be useful is also rich enough to say utter nonsense that sounds, at first glance, reasonable. Race conditions are an example of that. And that's everything you ever wanted to know about AND states. If you found this video interesting, please click the like button. If you found it really interesting, click the like button a lot. If you want to be notified about upcoming videos on this channel as I publish them, please click the subscribe button. If you want to know more about UML or SysML, MBSE, model-driven development, please visit my website, bruce-douglas.com, for papers, presentations, models, and more. It's all free. Come on down. I hope you found this video interesting. And with that, have a nice day.